Good morning. So I'm going to show you how we can investigate the relationship between pressure and depth, static pressure, using an interactive simulation from University of Colorado. Just so we know, a reminder, pressure P, and again we are talking about static pressure because we also have a term that we call dynamic pressure when we have a fluid that flows. Static pressure is proportional with depth, h or y, however you want to call it. And the proportionality constants are density rho and gravitational acceleration g. So by rho, this Greek letter, what we mean is density. Now usually what we do, we measure pressure for a different depths for a specific fluid, meaning for a constant density, but the density could increase. We can compare pressure, static pressure for fluids that have different densities. And g is nothing else than 9.8 meters per second squared gravitational acceleration that all objects have in free fall, meaning speed increases by 9.8 meters per second each and every second. That's what we mean by an acceleration. Increases. Just don't type too fast. Okay, since we did talk a little bit about dynamic pressure, when we have a fluid that flows, that's proportional with velocity squared, and the proportionality constant is density rho. So it's 1/2 times density times velocity v squared. But this is the interactive simulation that you are going to use. You can have a ruler. Click on check this box, ruler. You can have different amounts of fluid. Yes, you can have fluid flowing, add fluid, and then you can check the grid if you want. You can have a ruler and you can measure the pressure at different depths using this atmospheric pressure. This measures atmospheric pressure, which should be 101.5 kilopascals. Here it says 106. In atmospheres, the atmospheric pressure, it's 1 atmosphere. You can have different units. Pound per square inch, 15 pounds per square inch is 1 atmosphere. You can turn the atmosphere on or off. No atmosphere means really no air. And you are going to perform pressure measurements using this pressure meter at different depths. So you can have the ruler. Yes, can you have 2 rulers? No. Okay, and you can measure the depth, the pressure at different depths. Yes, what you notice is that as depth increases, pressure increases too. Let's use metric system of units, kilopascals. Kilo means 1000, kilogram 1000 gram, kilopascal 1000 pascal. So this is 129,000 pascals, or 1 pascal is also 1 Newton per square meter. Just so we know. Yes, and by 1 Newton per square meter, what we really mean, Newton is unit for forces, for weight. A weight of 1 Newton that's placed on a surface area of 1 square meter, and that means 100 grams. So 0.1 kilograms times 9.8 would give you roughly 1 Newton. And if you place that on a surface area of 1 square meter, 1 meter long, 1 meter wide, 1 square meter, then you have a pressure of 1 Newton per square, 1 Newton per square meter, or 1 pascal. I said 1 pascal, 1 pascal, not 2. I typed 2. Okay, what else can you do? You can have vessels that have different shapes. Again, you can add water, you can get rid of some of the water, You can measure the pressure at different depths. As depth decreases, pressure decreases too, whether it's in atmosphere. Yes. This is actually total pressure. Pressure pressure which includes gauge pressure and atmospheric pressure. Atmospheric pressure is 1 atmosphere. Total pressure is at this depth, 5 meters, is 1.27 atmosphere, which means the gauge pressure due to the liquid is 0.27 atmospheres. What else can you do? You can change the fluid's density. What you are going to notice is that if you keep the pressure meter at the same exact depth, as you increase the density, pressure increases. As you decrease the density, pressure decreases. Honey has a higher density than water. Now, the older the honey is, the higher the density. Why? Because bees actually extract water from inside the honey as time goes by. You can also change gravitational acceleration. Of course, hypothetically, we are not going to go anywhere. Allegedly, there are astronomical objects that may have a different gravitational acceleration. If you drop an object on those hypothetical astronomical objects, it might take from like the same height, 1 meter for example, it might take different amounts of time to hit the ground. But you can change the gravity. Watch what happens to pressure. This is the pressure meter at the same exact depth. As you increase g, gravitational acceleration, from the formula we can see right away that if you increase g, of course keeping everything else, depth, h or y, however you want to call it, if you density constant, if you increase g, static pressure will increase too. And this is what we are going to see. You increase the gravitational acceleration, pressure increases. If you double gravitational acceleration, pressure doubles at the same exact depth. And you can play with this one, you know, double the gravitational acceleration but half the depth. You should have the same exact pressure at half the depth that you had at twice that depth when gravitational acceleration was half, if that makes some sense. It does, but what else can you play with? You have a fluid whose density could be changed. Yeah, gasoline, lower density than water. Gasoline floats in water. And in two different communicating vessels, you can measure you notice that the pressure at the same exact depth is the same. Yes. What else can you do? You can place a weight, and while placing the weight on top of the fluid in one of the vessels, you'll see that pressure does what? Increases, no? And the greater the weight that you are going to place, 500 kilograms, the greater the pressure. And this is what we use in hydraulic lifting devices like dental chairs. No, we also use that in the brake system in our cars. So a dentist actually exerts a very small force up on the brake pedal and it lifts up a huge patient. How can that be done? Due to the Pascal principle, which we did talk about, pressure gets transmitted undiminished throughout a fluid, and that's why with your own weight you can lift up your car. All you need is the car to sit on top of a piston that's on top of a cylinder whose cross-sectional area is greater than the cross-sectional area of the piston or the cylinder on top of which you are going to place your own weight. So with your own weight you can lift up your car. You do that using an incompressible fluid. Water is any fluid is practically incompressible, cannot be compressed anymore, and since pressure is at the same exact height, it's the same in these two communicating vessels, and the pressure gets transmitted undiminished, pressure not force, gets transmitted undiminished throughout the fluid, what you are going to have is pressure in the narrower cylinder being equal with pressure in the wider cylinder, as simple as that. And we are also going to play with an interactive simulation like that in another experiment. And since pressure is nothing else than pressure P is force F per unit area, that's why it's expressed in newtons per square meter. Force is expressed in newtons, area, surface area expressed in square meters. What you have is the force that you exert upon the narrow piston divided by the cross-sectional area of the narrow A sub n. It's equal with the force that you are going to place, which is the weight of the car, upon the larger piston F sub L divided by the cross-sectional area over the larger piston A sub L. Let's use capital L so we clearly see that. Another way of writing that is that if you multiply across, the force that's exerted upon the narrow cylinder times the cross-sectional area of the large is force that's exerted upon the larger cylinder times the cross-sectional area of the narrower cylinder. Yes, just multiply across. You go this one from denominator on the right hand side, numerator on the left hand side. You move this from denominator on the left hand side as numerator on the right hand side. That's all there is. Of course, this can also be expressed another way. Ratio of the forces, force over, let's use the same exact multiplication. We are just going to move this force exerted upon the larger, by the car, placed upon the larger cylinder piston from the right hand side to the left hand side. From numerator on the right hand side becomes denominator on the left hand side, and then we are going to place this cross-sectional area from numerator on the left hand side. This becomes denominator on the right hand side. So what you are going, denominator on the right hand side, what you are going to notice is that the ratio of the forces goes as the inverse of the ratios of the cross-sectional areas. Area of the narrow A sub n divided by area of the larger A sub L. Let me show you again that this picture. Yes, so you place the heavier object on top of the larger cylinder. So when you exert the force upon the brake pedal, right under the brake pedal you have a narrow piston, a narrow cylinder, and then you have the master cylinder which is placed next to the wheel, and that's why you can, with a very small force, you can stop a huge car. In other words, the force that you exert upon the brake pedal times the distance through which the brake pedal moves, which is force times distance is work, stops that work, stops the kinetic energy of the car. As simple as that. Okay, but this is another story. We said that we are going to use that in another interactive simulation, and I can show you that interactive simulation. But that's going to be a separate experiment, into which you are going to have to play with different cross-sectional areas. Remember that cross-sectional area of a piston, it's nothing else than pi times r squared. Area of a cylinder, cross-sectional area of a cylinder, is pi times radius r squared. Area of a circle. Cross-sectional area of a cylinder is a circle. But you are going to play with in another experiment with a different interactive simulation like this one, in which you can change the cross-sectional area, the radius of one of the cylinder, make it narrower, make it wider, and then you are going to try to figure out what do we need to place on top of the piston in the narrow cylinder such that you lift up a patient or a car. Yes, using the hydraulic lift principle. I'm gonna post a link to that one. We can yes, play with it. It's gonna be very similar to this one. You can change the radius, you can change the weight, you can change the it's just that this one does the calculation automatically, so you don't have to do much. Okay, I'm gonna find another one. Okay, so the purpose of today's experiment is actually investigating the relationship between pressure and depth, between pressure and density, and you'll be using an interactive simulation from University of Colorado.